Welcome back. So, a quick recap before we proceed further. The various equations that we have arrived at or we have formulated in the course of our discussions are presented in your first slide. The free field expression for the probability distribution n exponential minus h phi. H is the action is given by, for the free field it is given by mu 1 by 2 mu phi square. We also have the expression for the green functions as the moments of the distribution. The path integral or the generating function of the green functions is given here, and also how to extract the green functions from the path integral by taking successive derivatives is also here. We also have the expression for the path for the generating function for the connected green functions as log z of j, and we also have here the expression for the field function, which is the first derivative of the generating function for the connected green functions. For the free field, as I mentioned, the action takes the form 1 by 2 mu phi square. The normalization constant we found out is under root mu upon 2 pi, and the generating function for the green function works out to the expression in the red box. The generating function for the connected green function is given in the blue box, and the free field function is given in the green box. For the phi 4 model, we add an interaction term to the action given by 1 by 4 factorial lambda 4 phi 4, and then we expand this interaction term on the premise that the coupling constant lambda 4 is very small as a perturbation series. And on that basis we get the expression for the normalization, the new normalization given in the green box here, and we also get the expression for the 2nth green function, 2n point green function as the expression given on the slide, that is represented usually as h2n upon h0, where h0 is connected to the normalization, it is the inverse of the normalization. We then obtain the Schwinger-Dyson equations for the path integral given in your red box, Schwinger-Dyson equation for the specific case of the phi 4 field interaction given in the green box. Then we obtained the Schwinger-Dyson equations for the field operators. We obtained it in two forms given as equations 1 and 2 in the red box, and for the specific case of the phi 4 field we got the expression in the green box. The Schwinger-Dyson equation for the phi power 3 by 4 field is given in this slide. We have that extra term with the coefficient lambda 3, which is representing the phi 3 field in the action. Now, then of course, we also worked through the Feynman diagrams. We arrived at the Schwinger-Dyson equations using the approach of Feynman diagrams. So, writing down the Feynman diagrams, all possible Feynman diagrams excluding the vacuum bubbles, and then expressing them or evaluating each of the diagram, and we arrived at the Schwinger-Dyson equation through that modulus operandi as well. We found a very interesting conclusion that the symmetry factors that were incorporated in the Feynman diagrams on the basis of combinatorics turned out to be precisely the correct symmetry factors which were dictated by the physics content of the Schwinger-Dyson equation. Now, we move to the limiting or the classical behavior of the phi 4 field. So, we start with the phi 4 field in the loop expansion. We introduce the concept of loops by incorporating the parameter h bar into our into the Schwinger-Dyson equation. H bar represent powers of h bar corresponding to the number of loops in the Feynman diagrams. So, the equation in the red box has two expressions with the h bar in it, one corresponding to one loop component of the Schwinger-Dyson equation, and the second corresponding to the two loop component of the Schwinger-Dyson equation. Now, in the limit that h tends to 0, h bar tends to 0, we get the tree diagram, or the diagram which excludes all loop diagrams and consists only of tree diagrams. In that situation, this Schwinger-Dyson equation of the red box translates to the equation that is given in the blue box. Now, if you look at it carefully, this equation in the blue box is nothing but the derivative of the action, or rather if I use the action that is given in the red box at the bottom of your slide, take its derivative and evaluate it at the phi tree of j, I get 0. In other words, this equation in the blue box is representing nothing but the condition S dash of phi tree of j is equal to 0, where S phi, the action, is given by the expression in the red box. So, the no loop or the tree actions, this is the tree action, the action that is represented, that is shown in the red box, that we carried forward from the previous slide, the red box slide here. If I take this derivative with respect to phi and equate it to 0, I get precisely the expression, of the Schwinger-Dyson equation in the limit that h bar tends to 0. So, this implies that this expression that we have obtained here is the solution, the expression in the blue box here. The expression in the blue box here is the solution of the classical solution of the given action, which is here in the red box. But we took it, the important thing here is why we are able to say this is because h bar tending to 0, if we identify h bar with the Planck's constant and h bar tending to 0, then corresponds to the classical scenario, or the classical limit, as you may say, and therefore, when we take the limit h bar tending to 0, on the one hand it corresponds to the no loop expansion, and on the other hand we find that h bar tending to 0 reproduces the classical limit, and therefore, we can also infer that the tree diagrams represent the classical limit of the Schwinger-Dyson equation, or the tree portion of the Schwinger-Dyson equation represents the classical limit of the complete Schwinger-Dyson equation. Now, let us explore this a bit further. Let us do a saddle point approximation, or an expansion about the saddle point of the given action. Our action is given in the red box here. We obtain the stationary point by solving the equation which is given in the blue box, equating the first derivative of the action to 0, and we find, and then whatever by equating the first derivative to 0, the point that we get as the saddle point, let us call it phi 0, we expand our action S of phi around this action, this saddle point or the stationary point phi 0, and it takes the form given in the green box. Please note that the term in the first derivative is absent because of the condition imposed in the blue box here. The first derivative defines this saddle point, and therefore, when we are expanding around the saddle point, we will get no term in the first derivative, that term will be 0. And then we start with the path integral, and we write the path integral in this form, and now we expand our S phi in terms of the expression that is given here in the green box. Using this expansion in the green box here, we write out the expression for S phi for the path integral given in the red box here, and we absorb the first term S phi 0 with the normalization, because it is independent of phi, it is a constant and it can be absorbed in the normalization. We have a new normalization n dash, and what remains inside is given here, the exponent is given by minus 1 by h bar phi minus phi 0 s double dash phi 0. Of course, we are ignoring higher derivatives of s at phi 0. Now, this integral is almost a delta function. Why do I say that it is almost a delta function around the point phi 0? Because if you look at this the variance of it is clearly a Gaussian integral, it is clearly a Gaussian integral. If you look at the variance of this integral, the variance is h bar upon s double dash of phi 0, and keeping in view that h bar is very small, we find that this variance of this Gaussian is very small, and in other words it approximates, or it is very close to an impulse or a delta function. It is highly peaked due to the small h, and the maximum contribution therefore comes from the phi values that are close to phi 0, and you can express them as in the range phi 0 plus order of root h, that is phi 0 plus root h to phi 0 minus root h, which makes phi minus phi 0 whole square of the order of h bar. So, to compare, we have obtained two expressions. One expression we have obtained from starting from the action, quantum action, and we have obtained the expression expansion around the saddle point. We have got s dash of phi 0 equal to 0, and we also obtained that in the limit that h bar tends to 0, the tree portion of the Schwinger-Dyson equation, this is under the condition of h bar tending to 0, which is the classical limit. Therefore, phi trace j is the classical solution, as I have mentioned earlier, as well of the Schwinger-Dyson equation. If you compare 1 and 2, then what we find is this expression, the expression number 1 also gives us the classical solution. Now, the important thing that needs to be emphasized is that the path integral, therefore, the classical solution of the path integral or the classical trajectory would be determined by equation number 1, that is one part, but this trajectory is only one of an infinite number of trajectories that constitute the entire path integral setup. The various paths that contribute dominantly or that dominate the contribution to the ultimate path integral are paths that are in close vicinity of the classical path. The classic, you see, the point is as I mentioned in the context of quantum mechanics as well, the weight of each path is the same, but the important thing is that the path integral is dominated by paths which are close to the classical path, which are very near to the classical path. It's not one path, every path has the same weight factor, but there are a number of paths which are close to the classical path, which interfere coherently, constructively. That is the reason that the path integral seems to simulate to some extent or to a large extent the classical trajectory. But I reiterate once again that the classical trajectory is just one path, and the set of dominant paths consists of an infinite number of paths that are in close vicinity of the stationary path, the classical path, and because they are in close vicinity of the stationary path, minor change in the action does not cause any significant change in the phase, and therefore, they interfere constructively. That is the important part. Now, we talk about a new concept, which is effective action. The Schwinger-Dyson equation for the phi 4 theory is given in the red box here, of course, incorporating therein the loop expansions. In the limit h bar tending to 0, we have already seen that this equation reduces to this quantity. Now, we ask the question, is it possible to find for a given action, you are given a certain action S of phi, S phi of j or S phi, that has a full field solution given by the symbol phi j. This is the solution corresponding to this action. Can we find another action, let us say gamma phi of j, can we find another action gamma phi of j such that the classical solution, the tree level solution to this gamma phi of j reproduces the full solution phi j of the original action S j. That is the question that we attempt to address. And this is what the problem is depicted here. You have the quantum action S phi, it has the full solution phi symbol of j. This is the full quantum solution of the quantum action. This is what is given to you. We want to find a classical action gamma phi of j, obviously it will be a function of this phi of j, the full solution, such that the phi j that we have as the full solution of the quantum action represents the classical solution of this action gamma phi of j. So, that is the question we attempt to answer. So, we write the given full solution of the original action as S phi is equal to S 0 phi minus j phi, where S 0 is equal to the standard 1 by 2 mu phi square in the case of phi 4 theory plus 1 by 24 lambda 4 phi to the power 4. And because phi full j is a solution of this, it is a solution of this, therefore, we must have S dash phi full of j equal to 0 or S 0 dash phi full of j is equal to j. We arrive at the equation at the expression given in the red box, because of the phi full of j is a complete solution, is the full field solution of S phi. That implies that S dash of phi full must be equal to 0, and that gives us this result. Therefore, knowing the expression given in the red box, which expresses phi full as a function of j, we can invert it and we can express j as a function of phi full. Let it take the form given in the green box. Now, we want to obtain an action gamma phi of j such that phi full of j is the classical solution of gamma phi of j. Let us assume because phi full of j has to be a solution of gamma phi of j, we again have by stationarity requirement that gamma dash of phi full of j is equal to 0, which gives us the expression given in the green box. Gamma dash phi full of j is equal to 0 or gamma dash 0 of phi full is equal to j. This is what we get because of the stationarity requirement imposed on the action gamma phi of j, because phi of j is a solution of this action gamma phi of j. Now, from here what we get is, from the previous slide what we get is gamma 0 dash phi full is equal to j, and that gives us gamma 0 of phi is integral of d phi of j. From this expression we immediately obtain the expression given, but the integration is with respect to phi, the integrand is j, we need to change variables to phi. We already have the expression with us, we have this expression because of this inversion given in the green box here. We make use of this and we write j as y of phi of full, where j is equal to y phi full, which we had obtained by the stationarity of the quantum action. Right. So, now we do an integration by parts. When we do an integration by parts, what we get is the expression phi full y of phi full minus integral of d phi phi full dy by d phi, taking y phi full as one function and 1 as the other function. First function y as one function and 1 as the other function, we do an integration by part. First function y into integral of the second function minus integral of derivative of the first function into integral of the second function. So, now if you look at this, the first expression we have taken as it is, The second expression dy is equal to dj. So, we simply substitute this expression integral phi full d phi cancels, we get integral phi full dy, which is nothing but integral phi full dj, but phi full is nothing but phi is the field function, and field function is the first derivative of the generating function for the connected diagram. So, we can write phi full as dw upon dj, and of course, with the loop parameter h bar, and this whole thing simplifies to give us phi j minus h bar w. When you simplify this integral, you get phi j minus h bar w, where j is now a function of phi full, and this whole thing is called is a Lagrange transformation. Now, we come to a new topic, renormalization. This is one of the most fascinating topics that we encounter in quantum field theory. In the context of 0-dimensional quantum field theory, the approach is somewhat abridged, but nevertheless, it brings out the nuances that are associated with renormalization. I will go through it slowly, because it is a bit technical, but it is very fascinating. So, let us look at the mathematician's perspective of what we try to do in quantum field theory, and what we have tried to do so far in the context of perturbation expansions for finding out the green functions and connected green functions of the theory. The mathematician would view it as you are given certain inputs. The inputs would consist of the mass and the coupling constants of the theory, and using this mass and coupling constants, the mathematician would like to arrive at expressions for the various green functions, various connected green functions C1, C2, C3 and so on. So, that is the mathematician's problem, and that is what by and large we have been addressing so far. For the physicist, however, it becomes a slightly different perspective. From the physicist's perspective, what we have is we measure certain values of some connected green functions using scattering experiments. On the basis of those scattering experiments, we get experimental values of certain connected green functions. Using those connected green functions, the next step is we work out the parameter values, the bare parameter values of the inputs that go into the action, that is the mass and the coupling constants, various coupling constants, that is the second step. And then on the basis of those mass and coupling constants that we have estimated using the experimental results, we try to predict, try to work out the more connected green functions, and that is the, and then of course, we may arrive at expressions for higher order green functions, and experiments may then be devised to study or to work out or to calculate these higher order green functions and see whether they relate to or whether they coincide with the green functions that we have worked out, and find out whether the theory is correct or the theory needs some modifications or needs to be abandoned. So, this is the physicist's perspective on this issue. Having outlined the difference in perspective between the mathematician and the physicist, we in the form it's the physicist's perspective can be depicted here. We work out the experimental the certain number of connected green functions, say C1, C2, C3, C4 experimentally. We get experimental values. They form our inputs to determine the various parameters, the bare parameters of the action, and these bare parameters of the action which we worked out on the basis of inputs received from the experiments are then used to work out more green functions, and these green functions are then compared with further experiments to arrive at the veracity, accuracy of the theory. Now, the issue of renormalization arises because we do not, as we have seen, we do not or we are not able to exactly solve or solve the theory, even the simplest 5-4 theory in a closed form. We invariably use perturbation theory as a mechanism of estimating or approximating the green functions up to a certain level. Now, that raises the issue of the point at which the truncation of the green functions is done, a truncation of the expansion of the series expansion is done, at what loop level the various quantities are calculated, that is very important, and that any inconsistency there would be reflected in inaccuracy, and that is where the role of renormalization comes into play. Let us see how. Let us suppose that we worked out C1, C2, C3 and C4 at a certain level of loop, certain loop level, let us say at the pth loop level. We have got C1, C2, C3, C4 values from experiment. Using the expressions for C1, C2, C3, C4 at say the pth loop level, we work out the expressions for the various bare parameters of the action at the pth loop level, and on that basis we work out the values of the other connected green functions, say C5, C6, C7 and so on at the pth loop level. So far so good, and of course, then it can be compared with experiments and so on. Now, let us assume that it becomes possible, or somebody exceptionally ingenious is able to work out C5, C6, C7, C8 at the p plus 1th loop level, work out expressions for C5, C6, C7, C8 at the p plus 1th loop level. Now, the question then arises whether we can use the data at the pth loop level for mu and the coupling constants as inputs to the formula obtained for C5, C6, C7, C8 at the p plus 1th loop level, and that is where the question of renormalization makes its presence. The answer is no. If we are working out the connected green functions C5, C6, C7, C8 at the p plus 1th loop level, or if we have corrected, let us say C5, C6, C7, C8 from the pth loop level to the p plus 1th loop level, it is absolutely imperative that we use as inputs to those p plus 1th corrected C5, C6, C7, C8 the values of mu, lambda 1, lambda 3, lambda 4 and so on, that are also corrected to the p plus 1th loop level. That is fundamental. The loop level must be consistent, otherwise what will happen is we will end up with divergences, and these divergences will distort the results of assessment or evaluation of the theory. So, that is how the problem arises. Now, let us see, let us practically work out through a very naive example and see what actually happens. Yeah, we have got the 5-4 theory. This is an example, please note this. This is you got a 5-4 theory. There are only two parameters, m and lambda. M and mu are related. H bar is taken as 10 to the power minus 2. Now, working at the tree level, we have worked out the formula for C2 H0. H0 means that we are working at the tree level. So, we worked the formula for C2 is 1 upon m square. This can be done on the basis of the Feynman diagrams. C4 we obtain as minus lambda upon m to the power 8. So, to repeat, we are having a 5-4 theory. The parameters are m and lambda. H bar we have taken as 10 to the power minus 2, and the formula for C2 and C4 we know at the tree level are 1 upon m square and minus lambda upon m to the power 8. Now, because the theory involves only two parameters m and lambda, in principle at least two experimental measurements are sufficient to fix the parameters. We do the two measurements experimentally, and what we find is that C2 experimental, the experimental value of C2 is found to be 1 and the experimental value of C4 is found to be minus 2. These are input, these are on practically worked out scattering experiments that have given us these inputs. C2 experiment is 1 and C4 experiment is minus 2. So, obviously, these will not change. These are actually worked out through experiments done in the lab. Now, on the basis of these values, when we input into these equations, in the equations that are given in the green box, when we input those experimental values, we arrive at m at the tree level is equal to 1, lambda at the tree level is equal to 2. So, now what we do is we predict C6 at the tree level, and we find that it is given by 10 lambda square. Please note h bar is equal to 10 to the power minus 2. So, we predict C6 and we find C6 of at the tree level equal to 10 lambda square upon m to the power 14, which we find as 40. So, this is so far so good, everything is done at the tree level, there is no inconsistency, is fine. Now, what happens is, let us say we want to work out, or somebody has worked out the C6 value at one loop level. When the C6 values, that the 6-point green function is worked out at one loop level, the expression is found to be given in the red box here, and the value on the basis, now this is important, this is very important, value of C6 H1 on the basis of the parameters m and lambda worked out at the tree level, that is at H0 level, works out to 33.60. This is, please keep track of the figures. C6 at H0 was found to be 40, this was correct, this was the value of C6 at H0. Then we worked out C6 at one loop level. We used the formula for C6 worked out at one loop level, but we inputted the bare parameters of the action into this formula, which were worked out at the tree level, and we found the value to be 33.60. Right. Now, what we do is we go right back and we go back to C2 and C4 and we correct our C2 and C4 formula, which were earlier at the tree level, and we rework them out at the one loop level. We work out C2 and C. Please note, these are not the experimental values. Experimental values continue to remain what they are. The formula for the C2 and C4 are reworked, and we incorporate therein the correction due to the first loop, and we find that the corrections are given by for C2 we find the correction as minus h lambda upon 2 m to the power 6, and for C4 we find the correction to be 7 h bar lambda square upon 2 m to the power 12. We retain the experimental values as 1 and minus 2 that we started with. We input them into this new formula that we have derived using the first order corrections in H, and we find m H1 is equal to 0.995 and lambda H1 is equal to 2.056. So, these are two values that we have now obtained the bare parameters to the action corrected at the one loop level. And when we input these new parameters, the updated parameters, the revised parameters at the one loop level into the expression for C6, which is also at the one loop level, we get the expression of 38.92. Right. So, the discussion on this set of results I will take up after the break. Thank you.